All right, so I want to now have us learn to use a different table in our textbook. This is only for air, and it is a convenience, so it's not always going to be available to you, but it is so convenient when we get to working problems with cycles that you're going to find it in most thermodynamic textbooks. So in your book, it's on page 763, and it's a table of relative pressure and relative volume. Now, these have no physical meaning. These are not related to any volume you would truly measure, okay? So you're going to see that they have no units. They are going to be tabulated for just functions of temperature, okay? So this is a lowercase r in your book. The uppercase r subscripts were reduced temperature and pressure we used when calculating compressibility factors to determine whether something really is an ideal gas. At this point, we have assumed that it is an ideal gas, and we have these new weird quantities. So, what is this? Well, there are a lot of processes that we are going to say are reversible and adiabatic, and therefore isentropic. If so, then delta S is 0, which means that using the tables, I would have to set this equal to 0. That's not totally trivial to do. It's not impossible, but it's kind of a pain in the neck. So what I can do is I can set this equal to r ln of P2 over P1. I can take an exponential of both sides, solve for the P2 over P1, and I end up with PR2 over PR1, which is a quantity that relates to temperature 1, a quantity that relates to temperature 2. Okay? So, I could also do the same thing if I had volume information. Now recall that volume I would be getting from the ideal gas law, but I can relate it to temperature using the C sub V dt integrals. Okay? Now, this is actually a very useful result. It's not essential because I always have this fact. Delta S is ST2 minus ST1 minus RLN of P2 over P1 set equal to 0. But this is a very convenient way for solving only reversible, adiabatic, or isentropic process problems. Okay? So, let's take a look at this. So air at 660 kilopascals at 1100 Kelvin expands isentropically to 660 Kelvin. What's the final pressure? So let's take a look at this. If I use these tables, I can, at 660 Kelvin and at 1100 Kelvin, I can look up values of PR. I just simply look them up. I'm not doing any calculations. Therefore, P2 over P1 equals PR2 over PR1, or P2 is P1 times PR2 over PR1. Therefore, I just take the ratio of these pressures, of these relative pressures, and multiply by the actual initial pressure to get the final pressure. I could have also done it using this equation. So I would have looked up the S's and then subtracted off 0.287 ln of P2 over the initial pressure. I would get exactly the same answer, but I have to do more work. So if this is available, this is certainly a time saver. So let's do this from 660 Kelvin and 660 kilopascals and 1100 Kelvin, expanded reversibly and adiabatically to 110 kilopascals. Okay, so now I know the final pressure. I want to know the final temperature. So a little different than the previous one. So again, I can find, if I know the temperature, I can find PR. So I look up PR at 1100 Kelvin. We had just done that, in fact. I know the initial and final pressure, so take the ratio of those, and I can solve for PR2, which is 22.37. But this has no physical meaning. But it allows me to now go to the table and interpolate to come up with a final temperature of 693.3 Kelvin. Okay, this is again a time savings, and it's very, very helpful as we get to doing more and more complicated problems. So what if I had reversible processes that had constant C sub P or C sub V? Well, I've got the same sort of thing going for me, but I have this relationship. K is Cp over Cv, and Cv equals Cp minus R. So I can relate Cv and Cp to K and R. R is, like I say, for air, usually 0.287. K for air at room temperature is about 1.4. And so I can come up with estimates of Cv and Cp using these. Now, if I do this with these definitions at delta S equal to 0, I can end up plugging them in here and solving for dt, okay, from the ideal gas law. A little bit of rearranging, just some algebra, really just some algebra, and then integrate both sides. Okay, I'm going to get a natural log of V2 over V1, natural log of P2 over P1. Use the law exponentials or laws of logs to undo that mess, and you end up with this expression here. Now, way back, we had polytropic processes, and I said, really, legitimately, these do happen? Here we go. This was our first case of a polytropic process. PV to the K power is constant, or P1V1 to the K power equals P2V2 to the K power. So our polytropic process, in one special case where the polytropic index is K, the Cp over Cv value for an ideal gas, is going to be a reversible and adiabatic process with constant C sub P's. So we'll pause there. We'll come back and look a little bit more at reversible processes.